Hi class, today we're starting chapter 7 and we are learning about vectors as force and velocity. So those of you who are more familiar with physics, this will be mostly a review for you. But chapter 7 is all about how we can apply vectors to different things in the real world. So this is kind of our start. So I put force and velocity together today for you guys. So yeah, this is mostly an application of what we have already learned. So a force is that which changes the state of rest or uniform motion of a body. So force is basically anytime there's an effort or exertion that's causing something to move. So talking about force just as a magnitude wouldn't make sense. So force actually includes the magnitude of the force, but also the direction of that force. Okay, are you pushing against somebody or down on something, or the force of gravity being pulled down or pushing something up? Okay, pushing and pulling has a direction and a magnitude of the amount of force. So therefore, it is represented by a vector because it has both magnitude and direction. So on Earth, we measure force in something called newtons. Okay, and so a newton is represented by the capital letter N. And you figure it out, if it's 1 kilogram, then it gets multiplied by 9.8 meters per second squared, which is the acceleration due to gravity. So therefore, you get 9.8 kilograms times meters per second squared. Okay, so a 1 kilogram object exerts 9.8 newtons of force. That's an 8 there. 9.8 newtons of force. So therefore, a 2 kilogram object, you would multiply 9.8 times 2 to get 19.6. Okay, so however many kilograms you have, you multiply that by 9.8 to get however many newtons. And that's the force it exerts. So since force is a vector, the same rules apply, and forces can be drawn as vectors. So that's going to help us in our problem solving. Now, the resultant of several forces is the single force that you can use to represent the combined effect of all forces. So let's say something again like a tugboat is pulling a boat. One's kind of in like more of like a southeast direction and one's more of a northeast direction, but they're both pulling. So the resultant would be where the boat actually goes. Okay, or if you can imagine having your arms out and you have two people pulling. So the stronger person is going to be pulling you. You're going to go more towards that person. So think about that as a vector. That would be a longer vector since they're exerting more force than the less strong person. And so the resultant vector would be closer to that vector because of what we know about the addition of vectors, the parallelogram law, if you can visualize that. So if you have two forces that are collinear, then the resultant is just the combined effect of those two forces. So imagine you have two people pushing a rock or a car or something, and they're right on top of each other, pushing in the exact same direction. The force is just going to be the combined effect of those two forces. You just add them together. But if the directions aren't collinear or the same, then that's where we use the triangle law or the parallelogram law to find the resultant vector, and that's the combined effect of all of the forces. Okay, so the individual forces are called the components of the resultant, and that's what it says here in the note. So in my car example, the components would be the force that each person is exerting on the car, or in the tugboat example, what force each tugboat is exerting on the boat. And the resultant is where the object actually goes. And then it's important to know what the equilibrant is. So the equilibrant, I never know how to say that. And that's the single force that would oppose the resultant. So if that one force was applied, then you would be in a state of equilibrium. That would just mean that maintain the object at a state of equilibrium. It wouldn't move. And so that is an important concept. So if you have collinear force vectors as drawn here, so we would call this F1, but we have the vector symbol above it, and this could be F2, so our two force vectors. Then this is the resultant, and it is formed because it's F1 plus F2. Okay, it's the sum of those two vectors, so it's the same direction, and you add the magnitudes together. And then this is the equilibrant. So notice it's the same magnitude as the resultant, but just in the opposite direction. So this is the negative of, I should put brackets around here, F1 plus F2. So the equilibrant and the resultant are opposite vectors. Excuse me. Okay, if they're non-collinear, then if this is force 1 and this is force 2 and they're placed tail to tail, then the resultant is this diagonal, as we know from chapter 6. Okay, and just like this is theta, we know that this is 180 minus theta, as we learned. Now the equilibrant then is the same magnitude as this, but just in the opposite direction. So this is the equilibrant. So it should be the same magnitude as the resultant. It's just in the exact opposite direction. So really this should just follow like a smooth line. So we can say that's negative capital F if that's the resultant force vector. And we can also denote it as E, the capital E, it's the equilibrant. So we can say here that F1 plus F2 is often denoted as capital F, the force vector. So these are called the components, each one separately. Okay, and this is the resultant, as we know. Okay, it says resultant. And when you talk about the angle between them, it always refers to tail placement. Okay. Okay, so there's some visuals for you. All right, so now if forces are in equilibrium, these vectors form a linear combination, okay? And if they are non-collinear, they form a triangle, okay? So basically, three vectors in equilibrium are in a rested state, they get back to themselves. So in this case, you would have A plus B plus C equals 0. Okay, that's because the resultant of A plus B would be negative C. So you're really adding the equilibrant to A plus B. So your force is kind of getting back to its home state. So everything is in equilibrium. So A plus B equals negative C is how you can think of this. So your force vector here, your resultant force is being opposed by this equilibrant to keep it in equilibrium. So A plus B plus C equals the 0 vector. Okay, now notice that the magnitudes of A and the magnitude of B added together will be greater than the magnitude of C. Okay, but in this case, if they're collinear, so if this is A and this is B, to be in equilibrium, C has to be the equilibrant here. In this case, the magnitude of A plus the magnitude of B will equal the magnitude of C. Okay. So it's also useful to know how to resolve a vector into its components. So one thing you'll be asked to do is when you have two vectors, determine the resultant. But if you are given a single vector, the resultant vector, they want you to take that and decompose it into two components. So you'll see the example at the bottom of this page is an example of that. So if you have somebody pulling a rope at an angle, how much of the force is a forward force and how much of the force is an upward force? So it's saying out of a resultant, break it into its two components. So even though we can do component vectors being at any angles, what we want most likely are the perpendicular components, and these are called the horizontal and vertical components. Okay, so if we have a vector here, we'll call this F, just as our force vector, then it can be resolved into its two components. So this one down here, I'll change the color for, we call it F sub X, okay, because it's its horizontal component. Okay, this is the horizontal component. Okay, and here's the angle theta that it makes with the horizontal. So because this is a right angle triangle, we can use SOHCAHTOA. So the magnitude of our X here is just this, the magnitude of the force, the resultant force, times cos theta. Okay, this is just SOHCAHTOA rearranged. Okay, where theta is the angle the force makes with the horizontal. Okay, and then we can talk about our y component or our vertical component. So this is our vertical component. So now we use sine, okay, because sine of theta, so this is also Fy right here, right? These are equal. So sine of theta is Fy over F. So the magnitude of Fy can be rewritten as the force sine theta. Magnitude of the force sine theta. So again, these can be memorized, these two facts, but really, I mean, you guys know your SOHCAHTOA, you know your trig. I really find it just easiest to always draw this out and just think about it that way. Okay, so two forces, 20 newtons and 40 newtons, are at a 30-degree angle. Remember, this is always assumed to be tail to tail when they give that information. So determine the resultant and the equilibrant. So I'm not going to draw it over here because we want to be able to draw the equilibrant. So I'm going to kind of draw it over here, and hopefully that leaves enough room for you. So two forces, so we'll have I'm going to make my 40 Newton one going this way because it's longer. So here's our 40 Newton force, and this is half as long, right? So there's our 20 Newton force, and this is not at all accurate, but there's our 30-degree angle. So determine the resultant and the equilibrant. So the resultant, again, we have to make a parallelogram here, and here is our resultant force. It's the sum. So I will call that vector R. And then our equilibrant force is going to be this guy here, opposing it. Okay, so let's find our resultant first. So if this is 30 degrees, then this has to be 150 degrees since they have to sum to 180. Okay, so the magnitude of our resultant then, okay, we're using cosine law, so our square root of 20 squared plus 40 squared minus 2 times 20 times 40 times cos 150 degrees. Okay, and from this we get 58.19, and that's in newtons. And so then we need to figure out this angle here to talk about the resultant. So we use the sine law, so sine theta over 40 newtons. Is that wrong? Actually, sorry, we find this, I'm not saying this as theta, I'm drawing this as theta. I'll tell why in a minute. Okay, there you go, 40 over 40 newtons equals sine 150 over, our resultant there was 58.19. So again, we're talking about this as the reference angle. And if you go through and do the sine law and find this, you get theta is 20.1 degrees. So we can conclude that our resultant is 58.19 newtons. And 20.1 degrees from 20 Newton vector toward 40 Newton vector. Now, I could have done theta as I originally had it labeled there, but this way works too. Either way is fine, and I just had it in my notes this way. That's why I switched it. So when we talk about our equilibrant, remember that the magnitude of the equilibrant is equal to the magnitude of the resultant. So in this case, it is also 58.19 newtons, except we have to find this, theta 2, to find out how to describe its direction. So theta 2 is, think about this, E and R are along a straight line because they're collinear. So theta 2 is going to be equal to 180 degrees minus theta that we found here. So in other words, 180 degrees minus 20.1 degrees. So it is 159.9 degrees. So the equilibrant is 58.19 newtons. And we can say 159.9 degrees from the 20 Newton vector toward the 40 Newton vector. Okay, counterclockwise. It's always a little bit awkward defining those when they're not given like a direction. Just find a way that makes it clear and just have a really good labeled diagram to describe which angle you're finding. But just remember that when you're talking about vectors, you need your direction as well as your magnitude. Okay, so hopefully this one makes sense to you. So Kayla is pulling a rope with a force of 200 newtons. So, I mean, if you go to page 358 in your textbook, there's a prettier drawing. I'm just going to show just like the vector diagram here. So it's making a 20. So if here's the ground. Oh my gosh, bad ground. Okay, let's try that again. If here's our ground. Okay, then here it's a 20-degree angle, so it's pretty shallow, but here's our rope. Okay, so the rope is being pulled with, and it's in this direction, 200 newtons of force, and it's 20 degrees from the ground. So we can break this into our vertical component, okay, which I will call Fy. And the horizontal component, which you can call F sub x. Okay, so our vertical and our horizontal component. So the magnitude of the resultant is 200 newtons. So think about it. Cos 20 degrees is going to be our F, the magnitude of Fx over 200. So therefore, if you just rearrange this, the magnitude of our horizontal component then is 187.9 newtons. Okay, so you can do it that way, or you can use the formula, like you can just go right to Fy is equal to 200 sine 20 degrees. Okay, so either you can use the formula like I did for Fy, or you can just kind of use SOHCAHTOA. Okay, so why does it make sense that there's so much more forward pull than upward pull? Well, because the angle is only 20 degrees with the ground, okay? So it's much closer to the ground, meaning that there has to be more horizontal pull than upward pull, but that's how you break it up into its two components. Okay, last force example, and then we'll get into velocity. So a mass of 20 kilograms is suspended by two ropes, making 60 and 45 degrees with the ceiling. Okay, so this is kind of like our ceiling. This is going to be not awesome on the trackpad, but I'll try my best. Okay, so we have 2 ropes. Okay, one is at a 60-degree angle with the ceiling. So 45, so I'm not, you know what, you might even want to get your protractor out for, and one is at a 45-degree angle to the ceiling. They don't really look that different, do they? Well, that's okay. So that's 45 degrees there. And this is 60 degrees here. Okay, and so this force is going up to pull it up to the ceiling, and this force is going up here, okay? So those are the 2 forces. And then you have this 20 kilogram object, okay? So 20 kilogram times 9.8 gives us that it is exerting 196 newtons of force. So this is something here that we call our position diagram. So we are going to redraw this as a triangle to create a vector diagram over here so that we can use it to solve for the tension in each rope. So if this is in a state of equilibrium, which it is, then the 2 components here, so I'll call this T1, so tension 1, and I guess I should keep switching my color. This is T2. They have to form a triangle, okay, in order for this to be in equilibrium. So I'm going to redraw. Here's my, oh man, Weens. I'm going to draw this here. So that is just my tension 1. I'm just redrawing it in a different spot. And then I'm going to move the T2 so that they're placed head to tail. So there's my T2. And that has to be making a triangle here with my T1 plus T2 equals the resultant. Okay, and the magnitude of this resultant is 196 newtons. So we think about this as 196 long. So how do we solve this? Well, let's fill in the other things we know, okay? We know that this is, if you put it horizontal here, this is 60 degrees. And this is 45 here, right? So using the Z pattern, that means this is 45 degrees as well. Okay, and this is a right angle. So we can actually just use SOHCAHTOA to find the tension in each rope. So I'm trying to keep the diagram here so you can see what I'm referring to. So just use wherever you need to on the page. Okay, so now we just use, to calculate it, we use the sine law, sorry, not SOHCAHTOA, the sine law. So notice that the magnitude of tension 1 is opposite 45 degrees. Sorry, now I'm confusing myself. All right, sorry. Didn't finish labeling the diagram. Okay, so we're thinking about this as a triangle. So because this is 60 degrees, this has to be 30 degrees, and this has to be 45. There we go. Okay, so this tension is across from 45 degrees. There we go. Confused myself for a second. Okay, and that is equal to 196 newtons, which is this one, across from 145 plus 60, so that's 105 degrees, so the sine of 105 degrees. Okay, and so you can just rearrange this and solve to find that the tension in that rope is 143.48 newtons. Okay, similarly, the tension in cable 2 is over sine 30 degrees. And then we can set it equal to our known ratio of 196 over sine 105 degrees. And the tension in the second rope is equal to 101 0.46 newtons. Okay, so those are the tensions in each of the ropes. Now, there is another method of doing this, which is on page 360, 360, and 361 of your textbook. There's also another example about equilibrium with forces. I've chosen to omit those for the sake of the video. If interested, I can present the components one in class. I'm saying this because in the past, everyone ends up using this triangle law anyways, so I don't want to overcomplicate something more than is needed. But if you're someone that is going into higher level physics and vectors, I would really encourage you to check out the other example. Okay, so that is force. So now I'm just going to do a little bit on velocity. So velocity is also a vector because it is speed and direction, okay? So if you're thinking about an airplane, the velocity of an airplane is its airspeed, and the velocity of the wind refers to its speed to the ground. So the resultant between those two is the ground speed. So what is a plane actually flying, right? Because you have to take into account the wind. So for instance, you can have a question like this. So a plane heads due north at 400 kilometers per hour. So we can represent that with a vector that's, with a magnitude of 400, whatever that means. So that can be our vector V. And it's blown off course by a wind that's coming at 100 kilometers an hour from the northeast. So we can represent that here. Here, it's coming from here, where this is 45 degrees. But we can redraw the vector here to show the sum, right? So if that's 45 degrees here, then this has to be 45 degrees here as well. So it's coming from the northeast. This is where the resultant is. So where the plane is actually going is the resultant, okay? Because it's being blown off course, okay? This is more exaggerated than it should be because this should be a quarter of the length as this. I drew it a bit exaggerated. So this we would call wind. And then this is our velocity plus our plane plus our wind. Okay, there's theta. So determine the resultant ground velocity. So how fast is the plane actually going? So think about it. It's actually going to be going slower than 400 because it's being opposed by this wind. And it's going to be going in this direction slightly, so north and then a certain amount of degrees to the west. So to find the magnitude or the speed of the resultant, we have to find the magnitude here. So we use our cosine law. Okay, so cosine law, as we normally do. Okay, and that gets us 336.8 kilometers per hour. Okay, and then to get theta, we can use sine law. So sine theta over 100 equals sine 45 degrees over our 336.8. So when you solve for that, you get 12.1 degrees. So we can say that our ground velocity is 336.8 kilometers per hour, and they're going north 12.1 degrees west. So you define it, you're going north and then that much to the west from the northerly direction. Okay. Then we have these types of examples with water flowing and a current, and kind of like if you paddle in a certain direction, where do you end up? So I'm just going to draw this picture as we go and like talk about the two different ways to look at it. So let's pretend these are the two banks, of a river. And Anna's driving a boat. So the river is 2 kilometers wide. Okay. And here we have Anna drives a boat at 20 kilometers per hour in still water, and she heads out from one bank in a direction perpendicular to the current. So this is the direction that she is going in. And then the current, we'll do by W, that's the water. Okay, we always assume it's flowing downstream. A marina drives lies directly across from the river from the starting point. So this is where she starts, and this is the marina. Okay. Where will the boat end up? Well, if she's ending straight, if she's going straight there, but the current's pushing her down, she's actually going to end up south of the marina, right? She's actually going to end up here. Oops, that's terrible. So this is the resultant of her boat and the water or the current pushing her boat. So where is the boat going to head up? Well, let's think about this. So this distance is 2 kilometers, but the magnitude of this vector here is actually 20. Okay, so the magnitude of v is 20 because that's its speed. And the magnitude of w is 6. So we can think about this as 20 and this as 6. But we also know that this is 2 kilometers. So we can use ratios to find out how long this w vector is. Okay, so we know that 6 is to 20 as our distance that we want is to 2. Okay, so this triangle to this is to this. So we can just cross multiply and get that we have 12 over 20 or 0.6. So the boat will land 0.6 kilometers south of the marina. Okay? How long will the boat take to cross? Well, that is the time of this resultant vector. So remember our distance, speed, time diagram. So if we can find the speed, we know the distance, okay, well, we can find it. If we can find the speed and we can find the distance, then we can find the time, okay? So we're going to use Pythagorean theorem using the 2 different lengths we know of the triangle, okay? So to find the speed, that's the magnitude of v plus w, which in this case is just square root of 20 squared plus 6 squared, which gives us 20.9 kilometers per hour, okay? It makes sense that it's going faster because it's being pushed. And then the distance, okay, so we're using the same triangle, but now we're just using the distances in this formula. So that would be 2 squared plus 0.6 squared. So we're using the same triangle, but the distances instead. So you get 2.09 kilometers. So the time is equal to distance over speed. So 20.9 divided by 2.09, which is 0.1 hours or 6 minutes. Okay, is the amount of time. Finally, what direction should the boat go if they want to land at the marina, and what speed should they go at? So now this is a different triangle. So now we want our resultant. So here's her start and finish. So now we want that the resultant is this. This is where we actually want the boat to end up. So think about it. Because she's being pushed downstream, she's actually going to have to head out in this direction, so that this plus the water is going to get her directly across at the marina. Okay, so in this case, your resultant, this that's actually the hypotenuse. So the magnitude of v plus w is actually the square root of 20 squared minus 6 squared. So she should be going 19.08 kilometers per hour. Okay, and then we can find this theta. Okay, and then sine theta is equal to 6 over 20. So theta is 17.5 degrees. So she should head 17.5 degrees away from the perpendicular, or west 17.5 degrees north, in order to end up at the marina. So there you go, force and velocity, they can be represented as vectors. Thanks for watching. Hope you learned lots.